So far, we covered the case of azimuthal symmetry. Which means that we can express functions that are functions of r and theta in terms of a useful way. What we haven't done yet is non-azimuthal symmetry, which are true spherical harmonics. And this is one of the few cases in this class where you're basically going to like kind of repeat a proof in some sense, like almost like a martial arts style exercise where somebody does something and then you just like mimic their movements. I think that's useful for going through one really important, really big separation of variables problem. And I'll just tell you what the answer is, but the homework problem itself is like you guys work out all the steps. And we've been kind of mumbling a little bit about all this Graham, Schmidt, Sturm, Liouville stuff, but I just want to explicitly state what sort of properties these things have. So this is where we're at so far. We can express functions of r and theta, so there's no phi. And the way we do that is sum from L equals 0 to infinity of A L R L plus B L R L plus 1. So that's the polynomial solution for the radial part. Remember, we separated stuff. So that's capital R of R. And then these funny guys, the Legendre polynomials, but of theta. So the claim is anything that you can write down that's a function of R and theta. There are some caveats on that. You notice these things have certain, differentiability and smoothness properties. You can't, think about the caveats we put on Fourier series. If you have something that has an infinite number of discontinuities, that's not going to work. But we're in a physics class, so we don't really have things like, I don't know, like ceiling function of x divided by x as x goes to 0, some wretched function like that. Okay, the way that you would think about this is if I have a function g of x and I can represent it in R notation, sum over n, an cosine n pi x over L plus bn sine n pi x over L. So Fourier series, right? So this is a Fourier series type object, but for spherical functions. Okay, any questions about any of that? Okay, what you guys are going to do is extend this to these things. So you're going to add phi. And I'll basically tell you what you get. But before we do that, there are a couple of really important properties. And again, realize that this is neat. So this is just like, for instance, Fourier series in the sense that if you tell somebody the ALs and the BLs they know everything. All they have to do is consult, the polynomials are easy, and then they consult the table of Legendre polynomials, less easy. But this is it, like all of the information of the function itself is encoded in this collection of coefficients. So this is really great. So I'm going to write an integral in terms of Legendre polynomials, and up to a constant, I want you guys to tell me what this is. And maybe this is the 30th time this has been asked, I guess. So the integral, remember, when we first derived this as the axial part of the solution to a Laplacian, we're acting on cosines of theta. And just for convenience, we made the change of variables from cosine of theta to x. So cosine of theta goes in between -1 and 1. So just shorthand, x goes in between. The variable x would also go in between -1 and 1. Okay, somebody tell me what you want this to be, and you're right, up to a constant.
To be 1 if the L and M are equal, and 0.
Yep. Yeah, so as concisely as possible, delta function, Kronecker delta LM. Okay, so there were two possibilities, and history chose neither. You could have defined the Legendre polynomials to make this super pretty, and it just is like pure delta function. Or you could have defined the Legendre polynomials to have, sorry, you could have defined the Legendre polynomials to have gross coefficients, and this was just delta LM. Or you could have defined the Legendre polynomials to have really pretty coefficients, and this is a mess. For some reason, history did neither. So the overlap of two Legendre polynomials is Kronecker delta times 2 over 2m plus 1. So that's like if they're equal. You know, the L equals M, so we could have picked L, could have picked M. I don't know why. Okay. Which means that so this means they're a basis. And this means any, with a little bit of a caveat, you know, they've got to be kind of smooth. Function g of x, we could use this the same way that we use a Fourier series. And we can express this in terms of Legendre polynomials. If g of x, or x, is in between -1 and 1. So less useful than a Fourier series, but you know, for things on a sphere, pretty dang useful. And we know that we can determine CL in the same way that we determined it in the case of Fourier series. Sorry, I'm right at the bottom of the screen. We can determine CL by taking the overlap in between the basis function and the Legendre polynomial itself. Right. So compare these to the integrals that you would get to find A and B for the Fourier series. So all of the concepts, the ideas that you onboarded to think about Fourier series and representing functions and kind of like overlaps and dot products, that all works here. This is just a different set of orthogonal complete functions. So these two properties, completeness and orthogonality, the orthogonality is here. So this is orthogonality. And that's essentially that PL and PM don't overlap. And this property is completeness. Is that we can represent any function. And again, think about vectors, right? So you could have a vector expressed in two different bases. One might be more useful than another one. So you can take a function and you can represent it in terms of its Legendre polynomials if you want. In the case of spherical polar harmonics, that's a great idea. Okay, so any questions about that? Okay, we made the first Legendre polynomials the hard way, And if that was like, if you were like 70% with the whole creation through Graham-Schmidt, that's pretty awesome. Mostly the reason to express it that way is so that these seem a little bit more sensible. And you can prove these, but the Legendre polynomials have actually a number of properties like this, but there are two that are really, really important. So one is called Rodriguez formula, is that you can make the Elf Legendre polynomial from scratch by taking a whole bunch of derivatives. And I always get the coefficient wrong. It's to the L factorial. Yep. Okay, that's the less obvious one. The more obvious one is the recurrence relation. Is that you can make, essentially what this is saying, you know, and I don't know, I guess it's not true, but I kind of always feel like there's a nicer way of writing this, is that you can actually make the Elf Legendre polynomial out of the subsequent ones. Schmitted them out in some sense. If you can find one solution of that differential equation and you know that the other ones are orthogonal to it, all you have to do is subsequently make each successively bigger one, right? So the recurrence relation, all of the differential equations that will do Hermite and Bessel, actually, I think that's about it. That's enough, I think, will have these properties. Okay, any questions about that? Just think about these as like properties of Legendre polynomials, and you'll be asked to maybe beat your head into one or two of them. Okay. Okay, ruining a little bit of the suspense is that when we break azimuthal symmetry and we want to express functions of r theta and phi, we're going to separate variables. And it turns out that separating variables like this is going to be a first step. So when you have three variables, just doing all three at once, you guys will do it. You'll see it gets a little bit sloppy. For various practical purposes, not the least of which is that sometimes you actually have information that only has theta and phi data. So if you're an astronomer, you know very little about R, how far away things are, but you know quite a lot at high precision about where things are angularly located on the sky. So we're going to split these things apart for various reasons, some cultural, some mathematical. These things, the Y's are called the spherical harmonics. And we're going to take them by themselves and talk about them for the rest of the day because they're really important. Okay. So this is going to be your fun weekend, is that you are going to take VR theta phi, and then you're going to try to solve the Laplacian. And of course, you're going to do that by separating variables. So R of R, theta of theta, and this is capital Phi of phi. And we already had it. There was a theta, a double derivative of phi term that we said is 0 because this doesn't exist. No longer doesn't exist. What I will tell you is that you should choose, when you separate stuff out, so there will be a lot of ... but you'll end up in a place that looks like this. So 2 derivatives of this thing equals a constant. Choose that constant to be minus m squared, please. Okay, if you don't, your life's going to be kind of annoying, and you can either be inspired or you can believe me when I say that this needs to be true. So the point of choosing the constant where all of the 3 separated equations are equal, choose it equal to negative m squared, where m is an integer in between minus L and L. That L was the L times L plus 1. It's the same sort of like refined argument, 150 years, people have figured out this is the nicest way of doing this. You will end up with this. And I'm not giving away anything because I'm about to show you a whole bunch of information about spherical harmonics on the internet. Okay, you could think about sines and cosines, because essentially what this differential equation is I'm saying, so put the big phi on the other side. What's the function that has 2 derivatives equal to the function itself up to a negative constant? Sines and cosines. Use the Euler formula. This makes life easier. So there are real versions of this, but just working with exponentials is much easier than working with sines and cosines. And as of 2 weeks ago, you guys are an adult and you can work with complex variable functions. Okay, so this is problem 1. It's you guys working through the steps of this, but these are the kind of belay points. This is where you should end up. Any questions about that? Because I think it got posted 2 days ago. I don't think anybody's probably started this, but you should end up here. So this is what spherical harmonics are. Spherical harmonics are just taking those 2 pieces of the solutions. And again, the reason for that is every once in a while you'll have, or every day of your life if you're an astronomer, you'll just have the angular data. So this is the notation. It's a little clumsy, but whatever. So capital Y, usually LM. So remember we had the integration constant, or the constant from the separation of variables L. M is the separation constant that people have figured out it's best to choose for the azimuthal part. Is going to be these 2 solutions with a constant in front. So there's just a constant in front. That's kind of going to be chosen to do orthogonality stuff. E to the I m phi. So that's the complex valued solution of the separated part of the azimuthal part. And then P cosine theta. The radial part, but it turns out this thing also has an m in it because we've introduced a new restriction by saying that L has to be in between an integer in between minus, m needs to be an integer in between minus L and L. So it turns out that when you match the 2 coefficients, you're essentially saying minus m squared or m squared is restricted to in between minus L and L. The Legendre polynomial needs to know what m is. So these things, the PLMs, or you might find them in a book as PLM of X, are what are called the associated Legendre polynomials. And you just have to match them. Okay. So what they have to do with the ones that we already know about is we ignored this piece. So P0L of X are the Legendre polynomials. So these are the ones you already know. And together, they let you do exactly what the other ones let us do is, let's say I have a function g of theta and phi. Imagine that you put chalkboard paint on a bowling ball and then you just like drew a function on it. Like you drew some, you know, like a heat map, some bright parts there, some dark parts there, some bright parts there. And it was like kind of a sufficiently smooth map. Anything, so this is a function g of theta and phi. So the value of the function, you tell me the angle, I tell you the value of the function. This can be expressed as a sum of spherical harmonics. So spherical harmonics are complete. Oops. And the problem with them is that there's a little sum inside the bigger sum, but aside from that, they work exactly the way that you would think they would work. Okay, so it's kind of the Fourier series-like thing, but for spheres, is that there's a coefficient, and then there's a function. Because we have two variables, the short story is because we got two variables, we have two indices, or quantum numbers, as we like to call it. Let me ask a question. What do you think this is? And if you can answer before I even finish writing it, great job. So there's one tiny little caveat, is that this is the complex conjugate. So slightly less obvious, but I have two spherical harmonics. They're complete and orthogonal, and I compute their overlap. And maybe their indices don't match. I got M and M prime and L and L prime.
Hopefully it's going to be some Kronecker delta.
Yeah, so we got Kronecker delta L and Kronecker delta M. And in this case, we did it right. So in this case, and this is actually part of the reason the Legendre polynomials are a little bit funky with that 2 over 2L plus 1 in their Kronecker delta. It's to make the spherical harmonics look nice. So these are orthogonal functions. If the indices both match, I get 1. If the indices, one or the other, any of them don't match, like an or statement, then they vanish. So this is really nice. Okay, so what we have to talk about is what d-sphere and sphere are, although we have done that. So let's say that I want to integrate over a sphere. And I don't know, let's just take some function, doesn't matter. Could be a spherical harmonic, could be not a spherical harmonic, it doesn't matter. I just need something as an integrand. So what is that? What are the limits that I need to integrate over?
you would need 0 to 2 pi for phi and 0 to pi halves for theta.
Yes, exactly. So the first thing is that this is a double integral because the sphere is a two-dimensional thingy. So this is integrated over the theta and the phi. So 0 to 2 pi for the phi, and then either minus pi to pi or 0 to pi, depending on whether or not you use the co-latitude or latitude. We use 0 to pi. So 0 is the North Pole, and then pi 180 degrees after is the South Pole. Okay, what is D sphere? Is D sphere just d theta, d phi?
You need the scale factors in there as well.
Yes, so I need the appropriate scale factors. So done this a few times, but not recently. So the one is, this is an area. We're actually computing the entire area for the unit sphere, essentially is what this is this is the unit sphere. So we need r d theta and r sine theta d phi. So this really is integral 0 to pi, 0 to 2 pi, f theta phi, r squared sine theta d phi d theta. And honestly, these should be flipped because of, I put the 2 pi, 0 to 2 pi inside. Okay, so scale factor. You'll actually see this written in a way because when you do a lot of spherical harmonic stuff, people get tired of writing this out the whole over and over and over and over. So you'll actually see sometimes is solid angle, this whole thing, a little bit of area on the unit sphere. Is defined as d capital omega. So you might see this at some point in your life. That is a two-dimensional integral because it's over a sphere, and that's solid angle. And what's true is that that's equal to 4 pi. So that's the area of the unit sphere. Okay, I'll do an example that's recorded, and then we'll do an example together in class. How about that? But first I want to show you like a couple of resources and why this is actually pretty neat. But any questions about this? At this point, things should start kind of like feeling like they rhyme. Is that we have a differential equation, we have some solution that comes out of it, the solutions have some properties. We're going to express functions in terms of decomposition in terms of those functions. Okay, Wikipedia, table of spherical harmonics. Perfect. So these are the L's, everybody uses L's. If you're scared of complex numbers, there are real spherical harmonics. You guys should not be scared of complex numbers. The first one is the Legendre polynomial 0, which is constant. And then this is just chosen, this particular constant is literally just chosen so that the overlap of y0, 0 with itself over the whole sphere is equal to 1. So if I square this, I end up with 1/4 1 over pi, which is the reciprocal of 4 pi. So these are chosen to be nice. Okay, L equals 1. L equals 1, I'm going to have 3 of these because for L equals 1, M can be -1, 0, or +1. So this is L equals 1, m equals -1. So all of these three are the spherical harmonics for L equals 1. L equals 2, I could have 5 of them, because for L equals 2, m could be 2, 1, 0, -1, -2. Okay, what you should see is that this has sines and cosines. The L equals 0 has sines and cosines to the 0th power. L equals 1 has sines and cosines to the 1st power. L equals 2 has sines and cosines collectively to the 2nd power. L equals 3, 3rd power. And you can see how these things get a little bit intense. Okay, the point is, if I pick this, L, y -6, 6, and I pick this, y2, 4, and I multiply them and integrate them up over the entire sphere, I should get 0. So they're perpendicular. So it's basically like the spherical Fourier series conceptually. So they're all worked out. You probably never have to deal with any of these. Let's look at why people care. Do you guys know what this is?
Those look like electron shells, maybe for like hydrogen.
Yeah, do you know what else they are? Just like straight up, they're spherical harmonics. Because in the time-independent Schrodinger equation that you solve to figure out where electrons would be in a hydrogen atom, there's a Laplacian. So there's del squared. And the second you see del squared for something that has spherical symmetry, you don't have to do any work whatsoever. You just start writing down spherical harmonics. So these are what the spherical harmonics look like in some sense. It's really hard to draw them with the radial component too, but this is constant. This has a sine or a cosine. This one looks like it has a sine or a cosine squared, right? To more lumps, sine or cosine to the 3rd power, we got 6 or 3 lumps, depending on how you count. So here's an example from astronomy. So this is the intensity of let's see, what are we gonna end up doing on this? I actually forget. Okay, so ultimately I think this is gonna be the temperature. Okay. So the temperature of the cosmic microwave background in the sky, which there's a lot of work that goes into observing and processing that, but just think about temperature of the sky just painted on the entire sphere of the sky. You can decompose that into spherical harmonics. This person is doing that laboriously. You see our old friends, Legendre polynomials. This is what they look like. Notice how they kind of look like the orbitals of a hydrogen atom, and you can animate them. So notice the scrolling, L5, and then M goes up to 5. The reason this person is only showing half is because the other ones are just kind of look the same. They're a little bit different, but kind of trivially so. And what you can see in the same way that higher terms of Fourier series are smaller and smaller wavelength, higher terms of the multiple expansion are smaller and smaller wavelength. Yeah, so this got all the way up to like 25 or something. Okay. And this famous image is essentially, this is the temperature of the sky, and this is the strength of that particular multipole moment. And so these are the sizes of temperature fluctuations, which actually are information about what happened, 30,000 years after 300,000 years after the Big Bang, when the sky became transparent. And there's a mystery in this. Like, they all seem to point in one preferred direction, which you wouldn't expect from like kind of a random process, which people are still puzzling through. But this is basically the size of the coefficient, so the C, and there's a peak at about, I think it's like something like 250 or something. So astronomers use spherical harmonics all the time. Quantum mechanics use spherical harmonics all the time. Anytime you have Laplacian in SPC, you don't even have to do work at this point. You just say the answers are spherical harmonics. So any questions about any of that stuff? We'll do examples and we'll, yep.
Oh, just for like that heat distribution, you would get that by like adding together the spherical harmonics for all the different coefficients that you like find experimentally. Is that what that like graph is showing? The like peak in the coefficients.
Yeah, it would be. So this would be a spectrum. So if I were to, I don't know, I'm on the internet. So so if I looked at, somebody just plays a note on a trumpet and I look at the Fourier series of that, this would be how strong each frequency is, so the amplitude of each frequency. And because it's a musical instrument, it's going to have like kind of nice, well-spaced peaks. So the idea is that, you play a musical note and then I ask how much of each type of sine or cosine I would need to replicate it, so make it from scratch. So what you're seeing when you see this is essentially that it's just there's so many of them that it's smooth, and the universe isn't a musical instrument with nice well-spaced peaks. So there is something there. So this wiggle does have to do with so-called acoustic oscillations in the early universe. So it's like the temperature of the sky is a little bit modeled. It's kind of dappily, like you can see there. And somebody literally just did the spectral analysis and said, well, how much of this low frequency is there? So how much of this low frequency is there? How much of this higher and higher frequency, in the same way that they spectrally analyze musical instruments. So this is kind of painstaking, and obviously it's got to be numerical integration because the data is discrete, but it's people backing out what the spectrum looks like. So sort of spectral analyzing the same way you do with music. And the kind of uncontested and neat thing is that the shape of this again tells you about the sort of the oscillating of the early universe, like this sort of plasma oscillating back and forth, and put some really strong constraints on the early evolution, so early cosmological models. The thing that's really weird is that multipoles point in a direction. So like a p orbital points in a certain direction, right? It doesn't have, like the hydrogen atom has no idea what a X or Y axis is, right? So it should be randomly oriented in a box of hydrogen gas. These orbitals should be pointed in random directions. In some sense, like who cares about the difference in between a PZ and a PX? But the universe apparently does seem to have a Z axis. And whether or not that's an artifact of the analysis or some weird thing where there's like a preferred direction in the universe, which would just bother everybody, hasn't been completely resolved yet. So it's like a 1 chance in 6 million that it happened. So that's the point at which people start like kind of sitting up and paying attention. Cool. Any other questions? You guys ready for a quiz? Yay.